All right. This lesson is how to take integrals using using partial fraction decomposition of rational functions. So in ABBC, you more than likely learned cases 1 and 2. There's actually 4 cases. So we're going to do a little review of cases 1 and 2, and then we're going to do cases 3 and 4, which you probably have not seen yet. All right, so let's start off with um, says homework to be determined in class. So that is no longer applicable because I have your homework assignment. It will be page, let's see, 492, 493, 492, 493. Wow, there we go. Numbers, just 4 problems. 9, 19, 24, and 35. So basically you're going to get 1 practice problem on each one of these cases. That there should be a 9. Better. Okay, so let's go ahead and review um, the idea of integration of rational functions by partial fraction decomposition. So the first one we're going to talk about is probably the one you've dealt with mostly. Case 1 is where you have distinct linear factors in the denominator and they are not repeating. So as you can see, the denominator of this integral is t plus 4, t minus 1. Those are both linear factors and none of them are repeated. They're not raised to any powers. So this is probably the most common one that you've seen. And the idea is that we need to break this up into a partial fraction decomposition. So it'll be a over t plus 4 plus b over t minus 1. And that has to equal this whole thing right here when we split this fraction here up, this rational function. Excuse me. Okay. So the idea is we are trying to find out what value of A and what value of B make this correct so that if we were to add these things back together using a common denominator, which is over here, these two things would add up and you would just simply get 1 on top. The idea is if you multiply both sides of this equation by the common denominator, t plus 4, t minus 1, this whole thing becomes 1 because you're going to multiply the t plus 4, t minus 1 on top. Those will go away, divide out, and you'll be left with 1. If you were to multiply this side, each piece by t plus 4, t minus 1, the t plus 4s are going to cancel out here, leaving you with a times t minus 1. And then here, if you multiply t plus 4, t minus 1 times this fraction, the t minus 1s will cancel out, and that'll leave you with plus b times t plus 4. All right, ignore that little thing down here at the bottom. Let's get rid of that. We'll do all that restart later. Hopefully it doesn't cause a problem in the middle of this. Okay, so the concept here is really pretty basic. You want to pick convenient values of t that's going to make one of these two things go away so you can solve for either a or b. Well, the first one that you should see is if I let t equal, let's start with this one, if I let t equal negative 4, so we'll let t, here, let t equal negative 4. If that happens, if I plug negative 4 in here, the b goes away because I get negative 4 plus 4 is 0, times b is 0. Plugging negative 4 in here is going to give us negative 5a equals 1. Solving for a, dividing both sides by negative 5, we get a as negative 1/5. That's going to be the value that goes up here. Then we can let t equal, well, let's see, if I want the a to go away, I'd have to plug a 1 in here for t. Plugging a 1 in here for t makes that 0. Plugging a 1 in here for t makes that 5b equals 1. And then dividing both sides by 5, we get b equals 1/5. So now what I've done is I've figured out a way to break up this fraction, this rational function right here, into both of these with negative 1/5 is a, 1/5 is b, and this is going to make taking the antiderivative of these two pieces much easier, because as of right here, not very simple to do unless we break it up into this. So I can now go ahead and rewrite my integral as negative 1/5 over t plus 4 plus 1/5 over t minus 1 dt. Okay, whoops, there we go. So hopefully you guys remember that if I have a constant over top of a linear function, when I go to take the antiderivative, it will be a natural log. So the antiderivative of this piece right here, the constant stays there, which is negative 1/5. The antiderivative of the t plus 1 over t plus 4 would just be the natural log absolute value of t plus 4. Likewise here, it's a linear piece in the denominator, so it's going to be 1/5 natural log absolute value t minus 1. And then, of course, it's an indefinite, so plus c. And there is absolutely nothing wrong with this answer. This is the correct answer. As you know, these natural logs can be condensed a lot of times, combined in several different ways. So what we can do is we can actually factor out the negative 1/5, just to show you that there are different ways that this could be written. And then this would be the natural log absolute value of t plus 4 minus the natural log absolute value of t minus 1 plus c. And then if you remember, I have a natural log minus another natural log. These can be condensed using division because it's a subtraction. So what I'll have is the negative 1/5 natural log absolute value t plus 4 over t minus 1 plus c. And just to let you know, again, this one right here, absolutely nothing wrong. This is the answer. However, getting it into this form is going to become something that you'd have to do in order to be able to possibly take a limit of this thing at a later time. And that played a part probably, I believe, in some of the series stuff that you guys would have dealt with. All right, in this case, this one is our final answer. Either one of these two are still correct, but this is probably the most common way that you would see it. All right. Case number 2. The product of linear factors, some of which are repeated. So again, you can see the denominator here has x minus 3 and x plus 2, but the x plus 2 is actually raised to the second power. X plus 2 is a linear factor, but it's raised to the second power, so it occurs twice. So while you don't see it written technically, this is x minus 3, x plus 2, x plus 2. So that's the common denominator. So when I go to split this one up, I actually have to write an a over my first linear factor, x minus 3, a b over my second linear factor, x plus 2, and hopefully you remember seeing this, the c part is over x plus 2 again, but this time it's over x plus 2 squared. Okay, and that has to equal the entire fraction that we had over here. So again, the idea is to multiply both sides by this entire common denominator, and when you do, you'll see that certain things would cancel out. The x minus 3's would go away here, so the a will get multiplied by x plus 2 squared. It's missing both of the x plus 2's. The b already has an x plus 2. It's missing an x minus 3 and another x plus 2. So b gets multiplied by x plus 2, x minus 3. And the c has both of the x plus 2's. It's missing the x minus 3. So when it gets multiplied, all we'll have left over is the x minus 3. And then multiplying the entire right side by the common denominator leaves us with x squared. So again, the idea is to pick convenient values that are going to make the a's, the b's, and the c's go away. So let's do that. Let's just go in order. We're going to pick -2. That's going to make not only the a go away, it's also going to make the b go away, because a -2 here gives you 0, a -2 here gives you 0. So we're going to be able to solve for c right away. So if I pick x equals -2, a and b are 0. Those are gone. C is going to be, let's see, -2 minus 3, -5 c equals, now you can't forget to plug the -2 in over here into this x. The last time we didn't have one, but this time we do. So -2 squared, of course, is 4, which means that c will equal -4/5. All right, let's pick another convenient value since we have our c. Let's pick 3, because that's going to make b and c go away. We'll be able to solve for a. So letting x equals 3, b and c go away, that's going to give us 5 in here, 5 squared. So we're going to get 25a equals 3 squared, which is 9. So a is going to be 9/25. And then the problem that we're going to run into is that we've already picked -2 and 3, and both of those made b go away. That is somewhat of an issue. So the best idea is to use the fact that we already know c and a. So we're going to plug a and c back in here, and then we could pick any other value of x other than these two, and we should be able to solve for b. So I'm thinking probably the easiest value to pick would be x equals 0. Maybe you come up with another one. It doesn't really matter. Any other value of x should work. If I let x equal 0, let's see, this is going to be 2 squared, which is 4, but I have to multiply that by a, and a was 9/25. Okay, we're trying to find b, which we don't have yet. But if I let x be 0, this is 2, this is -3. 2 times -3 is -6. And then c we have, which is -4/5. And if I put a 0 in here, that's going to get multiplied by -3, and that has to equal 0, because we're plugging a 0 in for x. So now we should be able to solve this for b. So let's see, this is going to be 36/25 minus 6b plus 12/5 equals 0. So 36/5, 25ths, and 12/5. We're going to have to put this into terms of 25ths. So that's going to become, let's see, multiplying by 5 on top and the bottom, 60/25. Actually, let's do this. I'm going to do multiple steps at once here. I'm going to add this 6b to the right-hand side. And then this is going to be a 36/25. So what we should get is 96/25 equals 6b. Dividing both sides by 6, let's see, what is 96 divided by 6? That's going to be, what is that, 16? So it looks like we get b to be 16/25. All right, let's see if this is going to work out. So now we've got a, b, and c. So let's actually kind of mark those off so that we can come back to them easily. There we go. All right, so now we can rewrite our integral. So we're going to have the integral of, if I'm not mistaken, A was 9 over 25, so I think that was 9 over 25 over x minus 3. Let me go double check that. A was 9 over 25 over x minus 3. Okay, good. B is over x plus 2, and B is 16 over 25 over x plus 2. And C is negative 4/5, and that was over x plus 2 squared dx. All right, these two pieces right here, the first two will be really simple to do because they're both just going to be natural logs. This one is not going to be a natural log. It is not linear. So we might have to do a very simple u substitution, and once you get used to doing a u substitution with something that looks like this, you'll realize that it's actually pretty easy to do the antiderivative. You might not have to do the entire u substitution to figure it out. So let's do the first two parts. Again, this will be 9 over 25, that's the constant, natural log, absolute value, x minus 3. This one will be plus 16 over 25, natural log, absolute value, x plus 2. This piece right here, all right, let's change colors for this. This piece right here, this is going to be a very simple u substitution. And as you can see, because the du equals dx, because of the fact that there's no coefficient out in front of this, this is going to be really simple. So when I rewrite the integral, or the fraction here, it'll look like this. And of course this is the same as negative 4/5 u to the negative 2 power. And when you take the antiderivative, you raise this power by 1, so that'll become to the negative 1, and then you divide this by negative 1, which will make that a positive. So what we really get out of this, go back to black here, is plus 4/5 u to the negative 1. But remember that u to the negative 1 is 1 over u, and u was x plus 1, so times 1 over x plus 1 plus c. You could obviously simplify this. You could distribute the 4, distribute the 5. You don't need to do any of that. We could try and figure out how to factor these things, maybe to combine some stuff. Again, you don't really need to do that. This, in this case, is probably about as far as we really want to go. Okay, hopefully everybody's following my u substitutions. I did not write the full thing out. I just kind of did a little work on the side there so that I could figure this out quickly. All right, let's move on. Now we're going to get to a couple of cases which you probably have not dealt with, and if you have, that's great, but if you haven't, this will be the first time you've seen it. So what's different about this one is, well, the first thing is it's not in the right form. First of all, we got a cube in the bottom, and we got a square in the top, which is okay, but we need to factor the denominator first. So we're actually going to rewrite the integral as 2x squared minus x plus 4. Factoring, looks like the only thing I can really factor here is the x out, so we'll have x squared plus 4 dx. So now what you can see is I have a linear factor of x, and then I have this quadratic factor. This cannot be factored any further. It doesn't factor into two linear factors. It's quadratic, and it's not reducible any further. So when you go to actually separate this one using partial fractions, it's got a little bit of a difference with the numerators. So the way this one works is I still have a over my x. The difference is over this x squared plus 4, because it's a non-reducible quadratic factor, the numerator is not just b. It actually becomes bx plus c. And that's the way it's going to work with a non-reducible quadratic factor, like this one is. And of course, that has to equal the entire numerator of the original over the denominator of the original. After this, it's the same basic concept. We're going to multiply both sides by this common denominator. It's going to get rid of the x here. We're going to have an x squared plus 4 multiplied by our a. The bx plus c, now you're going to have to keep that in a quantity. It's missing the x, so it's going to have to get multiplied by x. And that has to equal 2x squared minus x plus 4, because the entire common denominator will go away when we multiply both sides there. All right, this one works a little bit different, and the reason for that is because there's no easy value that I can make this 0, because x squared is not going to ever give us negative 4. We're not talking imaginary numbers or anything like that, so we can't just pick a value of x to make this work. So what you actually have to do is you have to distribute everything here. We need to get rid of all the parentheses, and then we're going to regroup. We're going to reassociate some of these things. So this will be ax squared plus 4a. This one's going to be plus bx squared plus cx, and of course that still equals 2x squared minus x plus 4. Alright, so here's what we need to do. We need to reassociate. In other words, regroup. I've got an ax squared and I've got a bx squared, so I'm going to regroup those two things in the next line. So that'll be ax squared plus bx squared. Okay, I only have one thing it looks like here with a c in it, with an x in it, so I'm going to regroup that one down here by itself. And then it looks like I only have one with just a constant. So I'll regroup that one by itself. And for right now, the right side just stays the right side. Okay, so hopefully what you can see is if I kind of reassociate these, whoops, here we go. This one I can factor out the x squared. And by factoring out the x squared, it's going to leave me a plus b x squared plus cx plus 4a equals 2x squared minus x plus 4. Here's what you need to understand. In order for these two statements here, this whole equation to be equivalent, whatever the coefficient of my x squared is here needs to be the same as my coefficient of the x squared here. So this a plus b must equal 2. Okay, this a plus b has to be equal to 2 in order for the x squareds to be the same. So down here, we're going to go ahead and set this up as a plus b equals 2. The c, which is the coefficient of the x, must be the same as the coefficient of the x here. Well, obviously this is a negative 1, so c must equal negative 1. That's kind of nice. That one's done. And the 4a here has to be the same as my constant. Well, the constant over here is 4, so 4a equals 4, meaning a equals 1. So now I've got a and c done. Because I have a, I can use that a value to plug back in here and solve for b. So since a is 1 plus b equals 2, subtracting 1 on both sides, b also equals 1. They don't always work out that easy, but in this case it did. So now we have our a, b, and c values. So now we can use those to go back up to this and plug those back in to be able to figure out how to take our integral. So let's go ahead and do that. So a is 1, so that'll be 1 over x plus, and then it's bx plus c, so that would be 1x minus 1 over, and it was x squared plus 4, right? X squared plus 4. And dx. All right, this piece, the 1 over x, that was probably the easiest one to do. This we're going to have to split, and we're going to have to use a little bit of ingenuity after this, and this is going to become a long one. I'm going to have to extend my page, so hopefully you guys are writing a little smaller. We're going to have to split this integral to be 1 over x plus, oops, I can squeeze it in there, dx. This is going to become x over x squared plus 4 plus negative 1 over x squared plus 4. All right, here's the reason we have to do that. This one right here, we can use a u substitution on. And don't forget, you can split the numerator over a denominator, but you cannot split the denominator up unless you go through a partial fraction, which is what we're doing. This one we can use a standard u substitution and solve. This one right here, hopefully you recognize as being very, very close, not exactly in the right form yet, but very, very close to the antiderivative that you would have to take of the inverse tangent, or this would be the derivative of an inverse tangent. So when we take the antiderivative, we're going to get an inverse tangent of some form. So it's going to take a little bit of extra work to get to that. And while you can memorize the pattern, if you have, that's great. I'm going to walk through the steps on how you actually figure this one out. So let's go ahead and do the pieces that we can quite easily. This is just going to be a natural log absolute value of x, so that'll be pretty straightforward. This one's going to require u substitution. So down here, we're going to do u equals x squared plus 4, du will equal 2x dx, and dx is going to be du over 2x. So for this piece, we'll get the integral of x over u times du over 2x. X's will go away. 1/2 integral 1 over u du. Integral of 1 over u is just a natural log, so we get a 1/2 natural log absolute value of u, but I'm going to go back up here and figure out what u was, x squared plus 4. Of course, I don't really need the absolute value because x squared plus 4 cannot be negative, but we'll leave it in there for right now. So this goes right here, 1/2 natural log absolute value x squared plus 4. Now we have to deal with the last part. This one's going to be a little bit more challenging. So if you remember, the derivative of an inverse tangent of x is going to be 1 over x squared plus 1. Well, this isn't 1, it's 4. So we need to make this a 1. The only way to do that is to factor a 4 out of the denominator. So when I factor a 4 out of the denominator, it's going to look like this. 1/4 x squared plus 1. All right, factoring the 4 out of the denominator, you have to factor it out of each piece, so that's why I get the 1/4 right here. Well, 1/4 x squared is still a perfect square, and we can rewrite that as 1/2 x quantity squared plus 1. All right, we can pull any constant out to the front, so I can actually pull the negative 1/4 out to the front of my integral, leaving us with 1 over, I'm going to rewrite this as 1 plus 1/2 x quantity squared. This is now in the right form of an antiderivative that we would be able to take to get an inverse tangent. However, we would have to do a very small u substitution here. And we would have to let u be 1/2 x du would be 1/2 dx, and dx is going to be 2 du. Now, you didn't really have to do that part if you understand that the antiderivative here is going to give you the reciprocal of the 1/2 out in front, which is that 2. Again, this is showing every step. This is not something you necessarily have to do if you've memorized the patterns for these. So if I've got this 2 right here, when I go and plug this back in, this is going to become 1 over 1 plus u squared times the new, oops, I forgot my dx's up here, didn't I? Fill those in. Times the new dx, which is 2 du. Bringing the 2 out to the front, multiplying by the negative 1/4 is going to give us negative 1/2 integral 1 over 1 plus u squared du. Okay, and this antiderivative will be negative 1/2. This is now in the perfect form for the the inverse tangent of u. But we're going to go ahead and go back to the original u, which is 1/2 x. So what I get is negative 1/2 inverse tangent of 1/2 x. That's the last part that's going to get filled in up here. Let's see, negative 1/2 inverse tangent 1/2 x. And this was indefinite, so plus c. Now again, there are some shortcuts. If you've learned those, that is wonderful. If you've memorized how to do the inverse tangent antiderivative, given something that is not already exactly in the form, something that looks like this one does right here, wonderful. It's going to save you a lot of time. If you haven't, this is the process you would have to go through. So it's a little tedious, but there you go. This would be our antiderivative using case number 3, which again has a quadratic factor which is not reducible, like this one was. All right, case number 4. Case number 4 has a quadratic factor which is not reducible, and it's raised to another power. So I've got a repeated irreducible quadratic factor. All right, same general concept to start with. This one's a lot more lengthy. So there's nothing I can really do on the denominator here. That much is for sure. When I go to split it up, a is still going to be over x. Because it's a irreducible quadratic factor, I have a bx plus c over x squared plus 1. And now, very much like the last time when we had a repeated factor of something like that, you got to do it again. So we're going to have a dx plus e over x squared plus 1 squared. And again, that equals the original fraction. All right, multiplying every piece here by the common denominator will leave us with an x squared plus 1 squared times a. The bx plus c has an x squared plus 1. It's missing an x and another x squared plus 1. So bx plus c times x times x squared plus 1. And then the dx plus e is missing just the x. And that has to equal the numerator over here, 1 minus x plus 2x squared minus x cubed. All right, this one's going to involve quite a bit more algebra up front here in order to solve for a, b, c, d, and e in this case. All right, so I think what we're going to have to do is we're going to have to FOIL this, expand this out. So this will be a times, let's see, it'll be x to the 4th plus 2x squared plus 1. I am assuming that most of you guys know how to FOIL that without too much of an explanation. This one's going to be a little lengthy here, so I'm going to do the bx plus c times x squared plus 1. I'm going to FOIL that out first. So that'll be bx cubed. Outer is going to be bx. Inner will be cx squared. Last is going to be c. And all that still has to get multiplied by that x right there. And then this one I can just distribute the x through. So that'll be dx squared plus ex equals. I'm going to rewrite this one. I'm going to put this one in descending order. So negative x cubed plus 2x squared minus x plus 1. All right, I'm going to go ahead and distribute this x through here, and then we're going to have to reassociate things. So I'm going to distribute the ax to the fourth plus 2ax squared plus a. Distributing the x through here is going to give me a bx to the fourth plus bx squared plus cx cubed plus cx and then plus dx squared plus, whoops, ex equals negative x cubed plus 2x squared minus x plus 1. All right, let's see. Let's reassociate some stuff here. I've got an x to the fourth and an x to the fourth. So if I were to reassociate those two things, I'm going to get an a plus b times x to the fourth, which has to equal the coefficient of x to the fourth over here. But I don't have an x to the fourth, so the coefficient of x to the fourth on the right side would have to be 0, because I don't have one. So I know that a, oops, erase that. I know that a plus b x to the fourth has to equal 0 x to the fourth, because I don't have any over here, which means a plus b must be 0. All right, that helps. Let's see. X cubes. I've got a cx cubed here, and I think that's it. Well, that'll help. So I've got cx cubed has to equal negative x cubed, which means that c has to be negative 1. That helps. That's finished. X squared is 2ax squared bx squared dx squared. So it looks like that means that 2a plus b plus d has to equal 2 from the coefficient here of the 2x squared. Okay, that doesn't help at this point because I don't know a, b, or d. So we'll come back to that one. X terms, I have a cx and an ex, so c plus e is going to have to equal the coefficient over here of negative 1. So c plus e equals negative 1. I do have the c value of negative 1, so what that gives me is negative 1 plus e equals negative 1. Of course, these two things are going to cancel out, which means that e equals 0, adding negative 1 to both sides. So now I've got two values. None of those really help me for this one. So let's see what we've got for our constants. Do I have any other colors? Let's see if this works. Yellow. It kind of works. Looks like a is my only constant. And a has to be the constant over here, which is 1, so that does help. A equals 1. So at least I have the a value that goes up in here. So let's see. I know, let's go back to black here, that a plus b equals 0. Here, let's fix that 0. That doesn't look good. So again, we know a plus b equals 0. I know that a Oh, yeah, that helps. I know that a is 1, so that means b equals -1. And now that I know b equals -1, I know a and b, so now I can find d. So let's see, we'll put this down here. 2 times 1 for a plus b, which is -1, plus d equals 2. So 2 and -1 is 1. Subtracting 1 on both sides gives us that d equals 1. So now I've got A, B, C, D, and E. That should be everything we need now to go ahead and rewrite this integral and take the actual integral. So let's see. The first one was just A over x. So that's 1 over x. Integral 1 over x. Plus. The next one was bx plus c. B is -1, so that's -x. C was -1, so -1, over the non-repeated irreducible quadratic factor x squared plus 1. Looks like we're going to have a very similar situation to what we did in the last problem there. And then the last one is dx plus e. D is 1, so that's going to be x plus e. That's nice. E is 0. And that'll be over x squared plus 1 squared. This one actually works out pretty nicely because that'll just be a straight u substitution. So it's really this middle term that we'll have to do the most work with, and we'll split up. All right, antiderivative 1 over x, natural log, absolute value of x. I already know I'm going to extend this, so I'm going to extend my page here a little bit and come back. This one we have to split. Integral -x over x squared plus 1 dx. That's a straightforward u sub. And then plus integral -1 over x squared plus 1. That's actually not so bad. Don't have to do any u substitution here. It's already in the right form. And then this one we'll have to do a u substitution. And I believe that the u substitution here and here is exactly the same. So we really only have to do it once. That will cover both of them. Really nice there. So u is going to have to be x squared plus 1 du is 2x dx, making dx du over 2x. So let's go ahead and take care of both of these at the same time. That should work out really nicely. All right. So natural log absolute value of x plus this one right here is going to be the integral of -x over u times du over 2x. That'll work out nicely. This one right here, I can actually factor the -1, not factor it. I can pull the -1 to the front of the integral because it's a constant. When I do that, it really just leaves a 1 right here. So that makes this negative, which is what I have here, and it makes this positive by pulling the negative out. 1 over x squared plus 1 is just the inverse tangent of x. And then this one right here, same u substitution, is going to become x over, in this case, u squared times du over 2x. All right, these x's will nicely divide out. So I've got the natural log absolute value of x. This one right here, I can pull the 1/2 to the front, integral 1 over u du minus an inverse tangent of x. This one I can pull the 1/2 to the front, and that'll become a 1 over u squared, which I'll rewrite as u to the -2 du. All right, almost done. Natural log absolute value of x. Antiderivative of this is the natural log absolute value of u, but u was x squared plus 1. Again, because it's x squared plus 1, not necessary to have the absolute value, but we'll leave it there. It's not wrong either. minus inverse tangent of x. This one is u to the negative 2, so raise the power by 1 is u to the negative 1, which is 1 over u. Divide this by a negative, just makes that a negative out in front. 1 over u is 1 over x squared plus 1 plus c. And there you have it. So obviously these can take a little bit more time because there's a little bit more algebra to do um, up front with the actual partial fraction decomposition. All right, you guys have 4 problems to do for homework, 1 of each case, and that should be it. All right.